Sorry, some technical issues have occurred. So we were telling if the addition of the nucleophile will result in the formation of a new stereogenic sender.
Your voice is not audible, madam.
Oh, sorry, maybe I might not have. Okay, now it is audible, right?
Yes, audible.
Yeah, sorry for the issues. So what we were discussing is that if the addition of a nucleophile will result in the formation of a new chiral sender or a new stereogenic sender, that sender where the addition have taken place is known as prochiral sender. So in the case of acetone, the addition of the nucleophile will not result in the formation of a new chiral sender. So therefore the carbonyl sender of acetone is not prochiral. Clear, right? Now when we consider this glycine molecule, glycine is having two hydrogens. So if we replace the green hydrogen with a other functional group G, which is having a higher priority than hydrogen, so we can label according to priority like NH3 plus will be 1, COO minus will be 2, G will be giving priority 3, and H will be giving priority 4. So 1, 2, 3. The rotation is anti-clockwise. So the new center that is formed is S. So here the green hydrogen or the green proton we can tell as pro S. Then if we are trying to replace the orange hydrogen, here with a group G that is having higher priority than hydrogen. So here if we give numbering according to the priority, NH3 plus will be 1, COO minus will be 2, G will be 3, and hydrogen will be 4. Here the this is anti-clockwise rotation, but hydrogen it is facing towards us. So the so instead of S, the new sender will be R. It will be opposite. When hydrogen is facing towards us, whatever stereochemistry we are getting, the opposite stereochemistry will be the correct stereochemistry. So this is the new sender that is R, and this orange proton it can be known as pro R. So these are enantiotopic protons, and depending upon whatever the chirality of the new sender, according to that we can name this hydrogens as pro S or pro R. Now we can see in the case of carbonyl compounds there are two phases. If we view from the side, and if we view from the side, like in plane we can write this carbonyl compound like this. Here if we are looking from this side, the hydrogen will be on our left hand side and the phenyl group will be on our right hand side. And if we are looking from this side, the hydrogen will be on our right hand side and the phenyl group will be on our left hand side. Accordingly we have written on the plane. Okay, so if we number this, oxygen will be having first priority, then phenyl, then hydrogen, 1 2 3 clockwise. So this is the re phase, and here the priority will be assigned like this: 1 2 3, anti-clockwise. This is known as the psi phase. So these are the two enantiotopic phases of this carbonyl compound of benzaldehyde. This is benzaldehyde. So these are the two enantiotopic phases of this benzaldehyde. So addition can take place from both re phase or from psi phase. Accordingly we will get different products. Okay. Now coming to Felkin-Ahn model. So if we are having a stereogenic sender that is adjacent to a carbonyl group, then then we will make use of Felkin-Ahn model to predict the stereochemistry of the product. Okay, the most important conformations of a carbonyl compound with a stereogenic sender adjacent to the carbonyl compound are those that place the largest group perpendicular to the carbonyl group. So this, when we are writing in the Newman projection form, we will be getting a number of conformations. Out of that, the when the largest group is coming perpendicular to the carbonyl group, that will be the most important or the lowest energy conformations that we will take for the reaction. So this is the stereogenic center we are having. L is the large group, M medium group, and S is the small group. So accordingly, we can write the Newman projections like this. So this is the first carbon, this is front carbon, this is the back carbon. So front carbon is having C double bond O and R, and this is the back carbon. Back carbon have the larger group that is perpendicular to the carbonyl, medium group and small group. And if we rotate this, such that the large group will come perpendicular to the carbonyl in this side, so the small group will be coming adjacent to the carbonyl, and the medium group will be away from the carbonyl like this. Okay, so these are the two conformations that we will consider for the reaction to take place. So the nucleophile can attack from 107-degree angle, that is the Bourguignon units angle. As you can see here, the nucleophile will be attacking from 107-degree angle with respect to the carbonyl, that is the Bourguignon units angle. So there are four possibilities, as you can see here. We have two structures and there are four possibilities. Nucleophile can attack from this side. Hello. The nucleophile can attack from this side. The nucleophile can attack from this side. The nucleophile can attack from this side, or nucleophile can attack from this side. So the lowest hindered path will be the most favorable part. Okay. The lowest hindered approach will be when the nucleophile will be attacking from this side, where the hydrogen, which is the less hindered group, is present. If it is, hello, if it is attacking from this side, then it will be close to pH. Similarly, the attack from this side will also be close to pH, and the attack from this side, it will be close to Me. So pH Me are considered like little bulkier groups compared to hydrogen. So this path, which is the unhindered approach, will be most favored. So this is the Felkin-Ahn model. Then we have considered if an electronegative group will be present adjacent to the carbonyl group, then this is the pi star orbital of the C double bond O, and this is the sigma star of the CCl bond. So these pi star of the C double bond O bond and the sigma star of the CCl bond can combine, resulting in the formation of a new molecular LUMO, which is a pi star plus sigma star. So this will be having lower energy compared to that of the pi star and sigma star. Hence the nucleophilic attack can occur easily here. Okay. As you can see, this is the pi star of C double bond O. This is the sigma star of CX bond. So if they combine, we will result in the formation of pi star plus sigma star, and here the antibonding orbital. This is the bonding orbital, antibonding orbital. Two will be formed. So this is the LUMO here. Okay. So since this is lower in energy, here the reactivity will be more. New molecular LUMO, which is having lower energy and hence more reactive. And when we consider this case, this is also a electronegative group. Here, if there is no chelation, we can write like this. The electronegative group we will write perpendicular to that of the carbonyl group, such that this formation of the new molecular LUMO will be taking place. Then here the attack can take place if there is no chelation, but in the case some chelation is possible, then this will rotate in this direction, resulting in the formation of chelation if ZnBH4 twice etc is present in the presence of only chelation metals. Okay, then the attack will be taking place from this side, so we will result in the formation of this product, which when we will redraw we will get this as the product. Okay, how to redraw we will see in the questions when we will discuss. So this is what was discussed in the module 3. So for references, you can follow Claydon Organic Chemistry chapter 6 and chapter 34. Now coming to the first question. For which of the following equilibrium, that is K equilibrium is less than 1? So different carbonyl compounds are given and hydration reaction is shown. So out of these four options, in one case, K equilibrium is less than 1. So which is that case? Hello?
Example 3, option 3.
Option 3 is the right answer. What could be the reason?
The more the two CH3 groups are electron releasing groups.
Hmm.
That's why the corresponding cation is highly stable.
Hmm. So, since
While
the two CH3 groups are present, it will be electron releasing in nature. So, the carbonyl center will be less electrophilic. So, the formation of this hydrate will not be that feasible in this case. But in the other cases, since the CF3, CCl3, fluorine, they all are electron withdrawing kind of nature. So, the carbonyl center will be electron deficient. As a reason, the hydration reaction can take place easily and it will result in the formation of this product. In this case, like this equilibrium will be more favored in this direction. So as you can see here, in the case of we have a carbonyl compound and we are adding water, so it will result in the formation of this hydrate. So in the case of acetone, the equilibrium constant K, it could be 0.001. When acetaldehyde is present, one of the CH3, which is the electron releasing group, is replaced by hydrogen, so the equilibrium constant value increased to 1.06. In the case of formaldehyde, both the methyl groups of acetone are replaced by hydrogen, so the equilibrium constant value even more increased to 2280. In the case of chloral, here one of the hydrogen is replaced by CCl3, so CCl3 is sort of a electron withdrawing group, so the value is 2000 compared to acetone. And when we consider hexafluoroacetone, here see, all the hydrogens of acetone are replaced by fluorine, which is electronegative atom, so the value even increased. As you can see, it is 12 lakh times it have increased. So the same structural features that favor or disfavor hydrate formation are important in determining the reactivity of carbonyl compounds with other nucleophiles, whether the reactions are reversible or not. Steric hindrance and more alkyl substituents make carbonyl compounds less reactive towards any nucleophile. So this is the factors that we have to consider when we will be seeing the reactivity. So steric hindrance and more alkyl substituents make carbonyl compounds less reactive towards any nucleophile. If electron withdrawing groups or small rings are present, then the carbonyl groups will be more reactive towards the nucleophile. So this is the factors that we have to consider. Clear? So as we have discussed, acetone plus water giving this hydrate will be having equilibrium constant less than 1. Any doubts? If there are no doubts, we can move to question number 2. In hexane 2,4-dione, how many different monoenols are possible? Option A 2, option B 3, option C 4, option D 7. Here they have not mentioned that all the protons are different or all the protons are equal. So when we consider the number of alpha hydrogens that are present, alpha hydrogens are the hydrogens that are present on carbon next to the carbonyl. So here 3 hydrogens are present, here 2 hydrogens are present, here also 2 hydrogens are present adjacent to the carbonyl. Hello. So when we consider the number of alpha hydrogens, the total number of alpha hydrogens will be 2 plus 2 plus 3, which is equal to 7. So there are total 7 alpha hydrogens that are present. So if we are considering each hydrogens are different, so 7 monoenols are possible after abstraction of the different hydrogens. So if we consider abstraction, in the presence of a base or something, or in the presence of acid also it can take place. O minus, double bond, then in when it will abstract proton from the base, it will result in the formation of enol. So this is how enol formation is taking place. So the number of monoenols formed will be 7, because 7 alpha protons are present in case of hexane 2,4-dione. Clear? Okay. Now coming to the next question. What is the correct order of equilibrium enol content of the following compounds? Correct order of equilibrium enol content of the following compounds. So, 4 different compounds are given, A, B, C, and D. And what will be the order? So, they have given 4 options. What will be the correct order of equilibrium enol content? Anyone? The right option will be option number D. We will see the reason. So, this is just for enolization. So the presence of at least one alpha hydrogen is required for enolization to take place, and enolization mostly take place in neutral or acid medium. So in some cases, enolates are formed in basic solution. So for this enolization to take place, the factors that we have to consider is hydrogen bonding, resonance, hyperconjugation, then like aromaticity, etc. These are the different factors that we have to consider while this enolization is taking place. So, in two tautomeric form of a compound, hydrogen bonding, resonance, hyperconjugation, etc., have the tendency to stabilize the enolic form. That's why presence of all or one of these factors increases the enol content of a compound or makes enol form more stable. So, we know that out of ketone and enol, mostly it is ketone that is favored. But in order for the enol content to be more, these are the factors that we should consider: hydrogen bonding, resonance, hyperconjugation, etc. So hyperconjugation, it depends upon the number of alpha hydrogens that are present in the compound. If number of alpha hydrogens are less, then hyperconjugation will be less, so the equilibrium enol content will be less. If resonance is less, then similarly enol content will be less. If hydrogen bonding is not possible, then enol content will be less. So coming to our different compounds, in compound A, hydrogen bonding is not possible, right? Here 6 alpha hydrogens are there, hyperconjugation is okay, but in this case hydrogen bonding is not possible as there is only one ketone. But in this three cases, hydrogen bonding is possible. So in B, C and D, hydrogen bonding will be possible. So A will be the least having equilibrium enol content. The compound having least equilibrium enol content will be A. Then out of B, C and D, when we consider C, it is having 8 alpha hydrogens, while B and D are having 1, 2, 3, 4, 5. 5 alpha hydrogen. This is also having 5 alpha hydrogen. Okay. Then out of so C will be the one which is having the most equilibrium enol content. From B, C and D, since the number of alpha hydrogens is more for C, so C will be the having most equilibrium enol content. Now coming to B and D, in case of B, this resonance is there. Okay. So this resonance will interfere with the formation of the enol. So because of that, B will be having least equilibrium enol content compared to D. Okay. So the right option will be C, greater than D, greater than B, greater than A. Fine. Okay. Now coming to question number 4. Predict the plausible products in the following hydrate addition reaction to 2-butanol. So 2-butanone. So 2-butanone is given and it is subjected to reduction reaction in presence of lithium aluminum hydrate. So it will result in the formation of some products. So what is the products? That is a question. Is it S2-butanol, R2-butanol, or a mixture of both S2-butanol and R2-butanol, or none of the above? Mixture of both. That is correct. Since there is no stereogenic center adjacent to that of this carbonyl, we cannot consider the Felkin-Ahn model. So, we can consider like LH is adding to both the rephase and side phase of this 2-butanol. Hence, it will result in a mixture of both S2-butanol and R2-butanol. So, this is the mechanism of reduction by LH. So, a hydrate will be attacking on the carbonyl center, and this oxygen will coordinate with aluminium. It will result in the formation of this intermediate. Since there are four hydrates, that is four hydrate that is present in one LH, so two more additions will be possible. So this will be the final intermediate. Then upon hydrolysis, it will result in the formation of this alcohol, 3 units of this alcohol. So the right answer is option C, that is mixture of both S2-butanol and R2-butanol. So this is clear, right? Okay. Now coming to question number 5. Among the following compounds, the one that will not show ketoenol tautomerism is. So four different compounds have been given, and out of which one is not able to show ketoenol tautomerism. What is that compound? B. What is the reason?
No alpha hydrogens.
Here one alpha hydrogen is present, right? But we can tell like even though there is a alpha hydrogen possible, the abstraction of this hydrogen will result in the formation of an alkene at the bridgehead position. So that is not favorable according to the Brett's rule. So this compound will not result in ketoenol tautomerism. Okay. So this is Brett's rule. Brett's rule is an empirical observation that states double bond can't be placed at the bridgehead of a bridged ring system unless the ring is large enough. So the bridgehead carbon cannot attain planarity due to the strain. So we can't place double bond there, as double bond makes the molecule sp2 hybridized, which should be planar. So since this is not a bigger ring system, so the even if double bond is forming, it cannot attain planarity. So that is why alkene that is adjacent to that of the bridgehead is not favored. So according to Brett's rule, bridgehead alkene is not favored. So in this case, the alkene that will be resulting will be at the bridgehead position. So here ketoenol tautomerism is not favored. In all other cases, there are alpha hydrogens that could be abstracted. Here also. In this case, the alpha hydrogen that is present, it is present at the bridgehead position. So abstraction is not feasible, as it will result in the formation of alkane at the bridgehead position. So option B is the right answer. Is it clear? Okay. Now coming to question number 6. Hemiacetals are usually unstable, whereas acetals are stable. Which has the most stable hemiacetal? Out of these four compounds, which is having the most stable hemiacetal? Option D. What is the reason?
Aldehydes and alcohols are present.
Hmm.
then the corresponding
It can result in cyclic hemiacetal kind of system, right? So that is
finally
not
the
stable.
cyclic histals are formed.
Yeah. So in this case, both alcohol and aldehyde is present in the same system. So this alcohol can add on this aldehyde, and it will result in the formation of
Finally, the chemical oxides are formed.
this lactol. So this is favored, and this is, and that is the reason why this is the most stable hemiacetal. In other cases, the formation of cyclic structures is not possible. So that is why it is less stable compared to option D. So this is how hemiacetals are formed, okay? So in the case of aldehyde, if alcohol is present in the medium, it will add on to the carbonyl, and it will result in the formation of this intermediate. Then this proton will be abstracted, leading to formation of OET. Then O minus, it will abstract proton from ethanol, and it will result in the formation of hemiacetal. So these are the different functional groups related to hemiacetal. If one alcohol and one OR is present, that is hemiacetal. If two OR is present, that is known as acetal. Then if instead of aldehyde, the addition is taking place to ketone, it is this is hemiketal. This is part of ketone, and if addition is taking place to ketal, this is hemiketal, OR2 and OH. And if R3 OR OR, this is known as ketal. And this cyclic hemiacetal, it is known as lactol. So these are the different nomenclatures associated with hemiacetals. So hemiacetal formation is reversible, and hemiacetals are stabilized by the same special structural features as those of hydrates that we have seen, right? By hyperconjugation, resonance, aromaticity, that features will be hydrogen bonding, that will be stabilizing the hemiacetals as well. However, hemiacetals can also gain stability by being cyclic. So this is the factor that is considered in our question. When the carbonyl compound and the attacking hydroxyl group are part of the same molecule, the reaction is now an intramolecular within the same molecule addition as opposed to the intermolecular ones. So that is the reason why it is gaining extra stability. Hemiacetals are being cyclic, so it is gaining extra stability. Fine. So the right option is option D. Any doubt? Okay. Now coming to question number 7. Predict the major product of the following addition reaction using Felkin-Ahn model. In Felkin-Ahn model, we have seen the ratio will be different, 3 is to 1 ratio. Sir, I have discussed now. Because of the presence of this adjacent chiral center. So one of this will be the major product. What is that? Option 1. Okay, we can see. So this is the two conformations of Newman that we have to consider while we are drawing the mechanism for this reaction. So according to Felkin-Ahn model, we have to place the larger group perpendicular to the carbonyl, and these are the two different conformations where the larger group that is coming perpendicular to the carbonyl. So there are four attack possible according to Burgid units angle, that is 107 degree. So the nucleophile can attack from here, the nucleophile can attack from here, the nucleophile can attack from here, the nucleophile can attack from here. So in this case, this will be the favored path. because here it is unhindered approach. We are having only hydrogen here. But in this case, it is closer to the phenyl group. Here also it is closer to the phenyl group. Here it is closer to the methyl group. So this is the least hindered approach. So this approach we will be considering. Now the nucleophile, in our case the nucleophile given is methyl lithium, so CH3 minus. So the nucleophile will be coming from this direction. So after attack, O minus will be forming. So the nucleophile will come here. Back carbon will remain as such. OH will be formed and this is hydrogen. And if we rotate it in such a way, if we rotate it in such a way as to view this, so we can if we are keeping the, so if we are viewing from this direction, you suppose the nucleophile and the phenyl group, both are coming in the plane. The methyl group is coming towards us, the OH group is coming towards us, and the hydrogen group, the hydrogen both are away from us. So this is the compound that will result. Okay, so we have been given these two options. So this, when we rotate 180-degree, just flip it. So this Nu will be coming, Nu will be methyl in our case. Okay, OH will be coming downside, methyl will be coming downside, and phenyl. Nu, which is equivalent to methyl. So this will be the right option in our case. Clear? This will be the major product. So the right option will be option B. Now coming to question number 8. In the following nucleophilic addition reaction, to a major product P and a minor product Q is formed, they are asking predict the major product that is formed. What will be the major product that will be formed? So here we have to consider the Cieplak model, because the carbonyl group is having an adjacent electronegative group, that is O, and this is TBDPS, tertiary butyl diphenyl silyl, TBDPS. And when we are using or treating with TBAF, this TBS group will be deprotected and we will get OH. So how we will draw this? So we can see the mechanism. So this is one of the model example of how the mechanism is taking place. So instead of NBN2, we are having OTBDPS. So it could be drawn in this fashion according to Newman projection. When we rotate it, we will get this NBN2. We should bring perpendicular to that of the carbonyl group. So if we rotate these groups, such that the unhindered attack will be possible, since there is hydrogen here. So it will attack in this fashion, and O minus will be forming. So we will get this, and if we will redraw it, we will get this molecule. Okay, so this we will rotate OCH2 OMe. So this we will rotate in such a way that the NBH2 will be coming in this side and this will be coming in this side. Okay. Accordingly, we will get this as the major product. And this TBAF, it is a fluoride source, and fluoride is having affinity towards silicon. Fluoride will go and attack silicon. It will result in the formation of this intermediate, and OR will be leaving. We will get this byproduct, and our alcohol will be resulting. So when we come to the mechanism of our reaction, so if we are seeing from this side, okay, here will be the hydrogen will, so if we draw the Newman projection, double bond O CH3. So if we are seeing from this side, the hydrogen, it is present on our right hand side. Any doubts? This OSiPH2TBU, that we can represent as OR, and this methyl group, it is present like this. So if we just rotate it such that the OR group will be coming perpendicular to the carbonyl, methyl, again rotate, CH3, methyl, OR, hydrogen, OR, methyl, hydrogen. This we have drawn. Me, OR, hydrogen. So this we can write like OR, Me, H. So this is the conformation that we will be considering, where OR is coming perpendicular to the carbonyl, hydrogen will be in this side and methyl will be this side. That will be the one we will be considering, conformation we will be considering. So this is the conformation that we are going to consider. Sorry. CH3 OR Me hydrogen. So this is our nucleophile. So this will attack in this fashion. So backside carbon we will write as such. This will be OH CH3. Fine. Now this two methyl groups. Okay. This group and this methyl group we will bring in plane. So we rotate it. One of the carbon we have to rotate. We will rotate this back carbon OH CH3. Back carbon we will rotate in this side. So Me will come here, OR will come here, and hydrogen will come here. Okay. So if we are looking in this direction, methyl is coming here, and on methyl the OR group is coming. That is away from us. So OR is coming away from us, and on the next carbon the OH is coming on our direction. So OH, and then this group. So the OR and OH are anti to each other. When we treat with TBAF, this OTB-DPS, OR is OTB-DPS, it will get deprotected and we will get OH, OH. Fine. So this will be the right answer. This we are just rotating and writing here. Fine. Any doubts? Okay. Now coming to the next question. Which of the reactions form the most stable acetal in the given reaction? So four different acetal formation reactions have been given, out of which is the most stable condition for formation of the acetal? B. Yeah. B is the right answer. What could be the reason? Here in B, here we can see this is ethylene glycol. So this can react and result in the formation of the cyclic compound. So as we have seen, the formation of the cyclic acetal is more favored. Hence this will be the most stable acetal compared to others. Here we will be getting OET, OET. Here also we will be getting OET, OET. Here also we will be getting. So this is the cyclic acetal that is forming. So the formation of cyclic acetal will be favored. Hence B will be the right option. So this is how acetals are formed. So we have seen the formation of hemiacetals in the previous question. So this is how acetal is formed. So we are having a ketone, alcohol will add on to that like this. It will result in the formation of this hemiacetal. Then what will happen? OH2 plus will be formed and this will be removed. So R double bond O R plus, then ROH will be adding, and we will get this acetal. So this acetal formation will take place in the presence of an acid only. Hemiacetal formation can be catalyzed by both acid or base, but acetal formation is catalyzed by acid only. So hemiacetal formation is catalyzed by acid or base, but acetal formation is possible only with an acid catalyst, because an OH group must be made into a good living group. We know OH is not a good living group. So for making it a good living group, like water, it can take place only in the presence of acid. Okay. So the right answer is option B, where a cyclic acetal formation is taking place. Now coming to the next question. So the major product formed in the following reaction is. So this is also a Cieplak model that is coming into picture. But here, since Zn2 plus is a chelating ligand, so chelation also we should take into consideration. So what will be the major product that is forming here? OMe will not be deprotected. So either A or B. Option B. Let us see. So this is one of the example where we can see the reversal in selectivity to that of the Felkin-Ahn model. So if NaBH4 is used for reduction, this is the major product that is resulting, and this is the minor product that will be formed. And if we are using a chelating ligand like this, the selectivity according to Felkin-Ahn model is getting reversed. So this, which was the major product, is now the minor product obtained in 1% yield only, and this, which was the minor product, now became the major product, which is in 99% yield. So for chelation to occur, we should consider two factors. That is a heteroatom with lone pairs available for coordination to a metal. So this is heteroatom, oxygen and O-methyl. Both are heteroatoms that can coordinate with the metal, and a metal ion that prefers to coordinate to more than one heteroatom at once. So in case of sodium, potassium, etc., it cannot coordinate with more than one heteroatom. That is why it is not showing any chelation. But in case of Mg2 plus Zn2 plus Cu2 plus Ti4 plus Ce3 plus Mn2 plus, etc., it can coordinate with more than one heteroatom. Hence, it can involve in chelation. Lithium plus only sometimes it can involve in chelation. Okay. So this is how the reaction is taking place. So we are looking in this fashion. Okay. So we can draw the Newman projection model according to Cieplak model like this. So the OR group should come perpendicular to that of the carbonyl group for the reaction to take place according to Cieplak model. And when the hydrogen is in this side, then the addition can, when the hydrogen is in this side, then the nucleophile can have an unhindered approach. So this is feasible. So this will result in the formation of O, OH, hydrogen, Nu, methyl, hydrogen, and OR. This is here the Me to Mg, the nucleophile is Me minus. Okay, so if we just rotate this, hydrogen nucleophile we can write like Me, OH, H, and if we will rotate this such that the methyl group will be coming Me, that is we are rotating in this fashion, OR and hydrogen. So as you can see here, what is pH? Oh, this was pH, not Me. pH Me, pH Me, OH. So this Me is Me over hydrogen. So if we are looking from this side, the pH and Me are in the plane, OR and OH are facing towards us. Okay, so that is why, as you can see here, the pH and Me are in the plane, OR and OH are facing towards us. That is, it is like in sin fashion, and Me is facing away from us, so it is below. This is according to non-chelation Felkin-Ahn model or Cieplak model. Now, when we come to chelation, for chelation, we have to rotate this OR such that it come close to this carbonyl and it can coordinate with magnesium. So the methyl group will be coming perpendicular to that of the carbonyl, and the hydrogen will be here, and nucleophile will be attacking from this side. So it will result in the formation of this product where both the OH or OR are anti to each other. So the complete reversal of the selectivity is happening here. Okay. So in our case, this is our question. We are having this starting material and ZnBH4 twice we are adding. So this is a chelating metal and hydrate addition is taking place. So what will be the major product that is forming? So we are having a carbonyl, OMe, we consider this methyl like hydrogen below, methyl above. So hydrogen will be, if we will rotate it, it will come like this. Me, OMe, hydrogen. Okay, now this will coordinate with zinc. OMe. Now the hydrate will be coming and attacking from this side, resulting in the formation of Me, hydrogen, OH, OMe, methyl. Sorry, this will be hydrogen, hydrogen. Fine. Then we will rotate in such a way that the medial groups are coming in the same plane. So we will keep the back carbon as such. Me, hydrogen. We will rotate this in such a way that methyl will come here. We will rotate in this fashion. Methyl will be coming here. OH will come here and the hydrogen will come here. Okay. So if we look from this direction, the OMe and OH are present anti to each other. So option B might be the right answer. Okay. OMe and OH are present anti to each other. Sorry, here they have written OMe and methyl. According to methyl group, it is considered. So we can consider according to that. According to the methyl group, when we are considering, see, this is the structure you have to consider. When we are looking from this side, okay, when you are looking from this side, this methyl and OMe are coming from the same plane. So you can look from this direction. This methyl and OH are coming in the same direction. It is facing towards us. Both are above the plane. This methyl and this OMe are present in the plane. So accordingly the answer will be, correct answer will be option A. So I have mistakenly written it option B by considering, by rotating this and considering this both methyls are in the plane. So option A will be the right answer. Option A will be the right answer. Any doubts? Okay. Now coming to question number 11. Which of the following has greater enol content than the corresponding keto part? So similar question we have discussed today. So which will be having greater enol content than the corresponding keto part? So the factors that you have to consider while considering the enol keto tautomerism. Keto enol tautomerism should be hyperconjugation, hydrogen bonding, resonance, aromaticity, etc. So here Option C will be having the greatest enol content compared to the corresponding keto counterpart, because here the number of alpha hydrogens are 1, 2, 3, 4, 5, 6, 7, 8 alpha hydrogens, as well as hydrogen bonding is also possible. So this will be having greater enol content compared to the other um, compounds that are given. Clear? So the factors that we have to consider is resonance, aromaticity, hyperconjugation, polarization, hydrogen bonding, etc. Any doubts? So the right option will be option C. There are no doubts. Let's move to question number 12, which is the last question of today's set. How many tautomers can be drawn for the following ketone? How many ketoenol tautomers could be drawn for this following ketone? Option B 2 is the right answer, because as you can see, only two alpha hydrogens are present. So abstraction of this will result in the formation of two enols. So option B2 will be the right answer. So this will be one enol counterpart plus this will be the second one. So these two ketoenol tautomers will be resulted. So is there any doubts regarding the questions that we have discussed today? Okay, if there are no doubts, let's wind up today's session. Thank you everyone for joining. Thank you so much.
Thank you, madam.
Thank you.